So we are all set and ready to go. Welcome. Welcome, everyone. And we have really exciting seminar for you scheduled today. The topic of today's seminar is auroral beads, an intriguing phenomenon which people have been studying and working to understand for many years, and provided a number of competing hypotheses. And we have two distinguished speakers from different types of the kinds of the community, but the same cinema team. So first speaker will be Shinatani, and then followed by Adam Michael, and we would like, of course, to have a lot of discussion at the end. So let's please hold the questions until until Adam's talk, and of course the chat is open as always. So thank you all for diving in, and Shin, please take it away.
Thank you very much for having me. Today I'd like to talk about auroral beads, and this is a kind of monologue or my confession that I do not understand auroral beads, and my intention is not to confuse you, but in case you are confused, Adam is giving a talk after me, so I am hoping that he will straighten that.
No pressure. Exactly.
Okay.
I know the question. So
I will discuss briefly 5 issues about auroral beads, mostly based on observations, especially auroral sky images. And auroral beads, as you know, are very often observed before auroral breakup. And it starts with a quiet arc, and all of a sudden it starts to beading or making a periodic structure. It evolves into spiral or undulation, followed by breakup, and the whole sequence is typically a couple of minutes, maybe several minutes at most. And Carmoni et al. Reported that for over 90% of onset arc, they identified wavy or beading structure. So it's very, very common. And because beading arcs are observed before auroral breakup, we discuss its formation in the context of substorm initiation. And the most popular idea for the generation mechanism of auroral beads is ballooning type instability, and whether it's MHD or peak simulation, or whether it's the earthward outflow of reconnection, or at the front of fast earthward flow, they simulated periodic structure and associated with auroral beads. And in a much larger scale, there was a simulation by Strassi et al. And based on combined model, high resolution global MHD and ring current, they reproduced the periodic structure in the transition region, and that can be another candidate or another way to form auroral beads in the near Earth region. And so ballooning instability, almost by definition, creates periodic structure, and it makes the configurational change of a near magnetic field. And so it's very, very consistent with the fact that auroral beads are observed before substorm onset. And there's another model of beads formation, which is based on the MI coupling, and the instability is called the feedback instability. And the feedback instability was originally proposed for explaining the formation of quiet arc. It's based on the phase matching between conductance enhancement due to precipitating electrons carried by reflected alpha wave and advective motion of ions, ionistic ions, due to convection. Though if you introduce Hall conductance and the zonal wave number, several studies show that they can produce a periodic structure, zonally periodic structure, and which they proposed as a cause of auroral beading. And so whether it's magnetosphere ionosphere coupling or magnetosphere proper instability, they have interpretation or idea that periodic structure reflects some kind of instability and driven by pressure in the magnetosphere or MI coupling in the MI system. And so the question is what or which one or none of them may be supported by observations, but I'd like to briefly review what observational issues or the fact issues that may not be explained in the context of these instabilities or what are outstanding issues. And those are the targets or focus of my talk today. And first, I'd like to talk about auroral beading in the context of turning of auroral streamers. And this is an event reported by Kepko et al. And here, in the field of view of ASI at Gilam, they identified equator-ward moving auroral forms. And you can take my words or their words. And there is a structure moving equator-ward just before auroral breakup. And we recently looked at the ground magnetometer data at two stations, actually, stations around the beading point. And what we found is that the H component, or its northward component, increased at Fort Smith here, but decreased at the Gilam right after the formation of equator moving auroral forms. And so it increase and decrease, and if they are caused by Hall current, which strongly suggests that convection is diverging from a meridian around here, and eastward and westward. And auroral beads formed just only on the eastward turning branch. And so indicating that the beading is not necessarily formed along the equator-ward moving convection flow, or if we project it not mapped to the earthward moving plasma sheet flow. Instead, in this event, beads formed after the deceleration or demarcation or divergence of the original earthward flow. So this is where auroral beads would map to the magnetospheric equatorial plane. And the beads forms, and as I said, it expanded westward and eastward, but along the eastward turning branch. And this is the first event. And we do have another event, but which happened on the westward turning branch. And this is the event, well, actually one of the three events, Nishimura et al. Reported in the earliest paper for the auroral sequence of subsystem initiation. And in this event, auroral streamer is coming down and made westward turning like that. And again, if you look at ground magnetometer data, on this side, we have, on this side, we have positive H disturbance. And for the Simpson and two other stations further in the east, they observed negative H disturbance around time started around the time of bead formation, the streamer turning, and followed by oral breakup somewhere here. So the anti-correlation of the H component disturbance on this side and on the other side indicate again that the earthward or equatorward ionospheric convection flow associated with earthward plasma sheet flow diverged around here, and the oral beads formed along the westward turning branch. And here I'm showing by evogram oral beads propagated and eastward, westward along the westward turning branch. And so beads do not form in the equatorward moving arc or at the demarcation point, but it formed after the breaking or deflection, zonal deflection of the original earthward flow. And another point I'd like to make, which is not today's subject, sometimes people associate substorm initiation with oral breaking, but that breaking would form current wedge type current system. But if you look at convection, the rotation of convection means divergence of electric field, and divergence of electric field would correspond to divergence or formation of or closure field and current. And therefore, the breaking related current wedge must form somewhere around here. On the other hand, the substorm initiated far off the demarcation point, indicating that the breaking is not necessarily the direct cause of the substorm current wedge formation. And so that's location about oral beading. And second subject is interhemispheric non-conjugacy. And this is a very famous event reported by Motoba et al. 2012. And they observed same these events, but in different hemispheres. Chornes is a station in Iceland, and Showa is a station in Antarctica. And so as you see that those two stations observed a very, very similar beading structure. And so beading, it observed conjugate stations. And from that, sometimes people claim that the source of beading is magnetic. But on the other hand, we had better be a little bit careful, because if the source is magnetic, we would expect the conjugate signatures. But the question is whether or not we can assume that the source is magnetic if we observe the conjugate observations. And in fact, for this event, we recently reported that the conjugacy actually break down in the middle of the evolution of oral beading. And here we are showing sequence, Chornes, Iceland in northern hemisphere, and the Showa in Antarctica. And the beading started at the same time in a similar way at the two different stations in different hemispheres. But in one station in Iceland, undulation started, but in Showa, beading stays. And this breakdown of conjugacy lasted more than 100 seconds, which is a very long time compared to the ultimate transit time between two hemispheres. And then in both hemispheres, oral breakup happened. So at least a part of the beading evolution, conjugacy breakdown, which strongly suggests that there is some contribution of ML coupling process. And that's the second subject. And I'm now moving on to the third one, which is about isolation or insulation of oral beading. And I'm showing 4 events here. And for each event, time goes from left to right. And in the middle, you see a beading. And the reason why those 4 events are special is that we do have two Auroral arcs side by side very closely. If you see, this is perhaps a good one. You see that the two arcs pre-existed before beading, and the beading started only along one of the arcs. And the separation between two arcs, it's just a fraction of degree, 0.2 degree or 0.3, 0.5 degree. But because despite this small separation, beading developed only along one of the two arcs and followed by Auroral breakup. So the scale of beading must be smaller than the latitudinal separation scale, must be smaller than the separation between two arcs. And if you map it to the equatorial plane, it corresponds to 1 to 10 proton gamma radius. It depends on the magnetic configuration, and it's stretched if the magnetic field, the equatorial magnetic field is weaker, but at the same time, proton gamma radius becomes larger. So if you normalize the separation by gamma radius, it will be just 1 to 10 times proton radius of the radii of typical energy protons in the plasma seed. And here I'd like to show you a movie, actually two movies. First one is for the event at the top left, and another one is the event shown in the top right. And the first movie, I'm hoping you can see it, but oh, it doesn't work. Maybe I have to stop. Okay. Now I hope you can see. It's not working?
No.
Okay, sorry. So I have to skip the movie.
Is it included in that supporting information in that paper?
But yes, so the original movie is included in the paper, and so
If you want me to, I can bring it down and while you're talking now.
okay. I appreciate that. So back to the slide. It worked on my computer. Slide show. No? Well, okay. I'm gonna move on. So the bottom line is that the latitudinal scale of auroral beading is a very tiny fraction of a degree, and that would constrain the modeling of bead formation. Okay. And this one, I'm pushing a little bit further, but here you see two arcs, and both arcs reveal wavy structure, but they propagate in opposite directions.
Should I download all of them?
Okay.
A lot of them.
Could you-
Which one do you want?
Could you actually title 3A,
S3.
figure 3A?
Oh, figure, not movie.
Not yeah, actually movie is 3, but showing 3A. Yeah.
Which one?
No, I cannot. Okay, here it is, 3,
This one, right?
3.
So
Yes.
S05.
Yeah. Could you upload it? Not that.
I
Could you
can
show
just-
it from
I
your
can just show
computer?
you.
Or maybe we can show at the end of my talk.
Yeah, whatever.
Okay.
I have it here.
Okay. And 3A, 3B, and 4.
Okay.
Okay, 4A. Sorry for the trouble. And yeah. And so there is another movie, but I'm hoping that Slavi can show at the end of my talk. So the beading is very, very small in latitude, and what I'm showing here is this is a study, Ramey study. They didn't call it beads, but it's very similar in the sense that they show periodic structure. And structure is moving on eastward along the poleward arc, but westward on the equatorial arc. And what they found is that those two arcs are located at the shoulder of one inverted V structure. And so if you consider the potential and assume that the potential has minimum at the center of inverted V, you expect that electric field is converging equatorward on the poleward side and poleward on the equatorward side. And the direction of the structure Auroral motion is consistent with the direction of the electric drift, as you expect from the potential structure. And so the convection seems to be very, very confined in latitude, but it's a part of larger scale inverted V. So you may wonder whether or not the associated electric field can map to the magnetosphere or plasma seed. And in fact, this is another event reported some time ago by Dubiagin et al. And in this event, they have first satellite passing by over the Scandinavian area and over a beading structure. And from poleward to equatorward, they observe electric field and the magnetic disturbance and particles. And as you expect, this spike of southward electric field, that corresponds to the beading arc. And if electric field is southward, E cross B drift is eastward. And this is what they observed as a direction of beading. And what is interesting, or what I'd like to emphasize, is that electric field is very, very spiky. But if you convert its potential difference from the electric field and the width of the spike, the potential difference is 100-ish EV, electron volt. On the other hand, the energy of precipitating electrons is above 1 keV. So the potential difference across beading arc is only a very small fraction of the field and the potential difference estimated from the precipitating electron, indicating that the small scale change or modulation or disturbance of MI coupling would cause structure corresponding to auroral beads. I'm not saying that's the cause of auroral beads, but the dynamics of auroral beading could be easily affected by the MI coupling. And that's why we have been interested in the propagation of auroral beads. And here I'm just comparing 3 studies, Carmoni et al., Nishimura et al., and ourselves. And what's most critical, crucial here is that the direction of beading propagation is predominantly eastward, as you see here. And so it's very, very puzzling eastward propagation. And if it's a ballooning type instability, you would expect ions as the primary contribution to pressure. And if that's the case, drift direction is usually westward. And for the feedback instability, we know that it's in the direction of convection. And again, if it's in the pre-midnight sector, the nominal convection, especially on the equator side of Harang discontinuity, it is westward. So despite those expectations, the actual observation shows dominantly eastward, this more distinct eastward propagation. And another feature is that this eastward versus westward propagation their distributions are organized by latitude. Westward propagation tended to be observed on the poleward side of the scattered points, and the eastward propagations, they tend to occur on the equator side. And so it's a big mystery for us. And I remember that Nishimura et al. In different studies, they proposed eastward propagation can be caused by localized, very small scale electric field in the plasma seed. If plasma seed is very, very thin, there's a charge separation between ions and electrons, and that creates vertical scale, vertical electric field, causing eastward equal speed drift. And also, I noticed that they also explained eastward propagation in the context of electrons carrying pressure. So there are possible explanations, but here I'd like to show you what's proposed, another possibility, which is completely different subject for today, but it's based on Rossby wave. And the Rossby wave is based on conservation of vorticity. And for us, the rate of rotation is higher closer to pole, as you know. At the equator, it's 0, and at the pole, it's 1 rotation per day. And if fluid parcel moves the equator or the poleward, and the total vorticity is conserved, the wave created and propagate in the direction depending on the gradient of the background vorticity. And so this is propagation, characteristic of propagation. And what I want to emphasize here is that the omega, that the frequency, is not the simple kx v0. Kx is a zonal wave vector, and v0 is a zonal flow velocity, but it's modified by this term. And this time, it depends on the second derivative of the latitudinal, the second derivative of velocity by latitudinal distance. And the first derivative corresponds to vorticity, and the second derivative corresponds to the change of vorticity. And depending on the ratio of the latitudinal structure and zonal wave number, the sign of the frequency or sign of propagation can be opposite to the flow direction. And of course, I'm bringing this up, assuming that, not assuming, but for all of these, we know that each bead corresponds to vortex motion. And if you have background flow, which is confined in latitude, confined in the sense that the scale is much smaller than the azimuthal wave length, which, as I showed you before, actually confirmed by 2 adjacent auroral arcs behaving differently, and that could create or cause bead propagation eastward or westward, depending on the second derivative of the flow velocity. So this is just the idea, but I'm hoping that somebody could test it if you have sufficient data. Or at least if we have satellite data over the auroral beads, that may be a good subject to test. And so I have been talking about auroral beads from different aspects. And in the context of cinema mission idea, I think cinema can contribute to better understanding auroral beads development and propagation, at least in 3 different ways. One thing is that I'm very, very curious or enthusiastically interested in the direction of bead propagation in the context relative to local convection. So by local, what I mean is arc scale. And so for that, we don't need any high resolution electric field measurements or convection measurement. It's just a matter of direction. And so the bead is extending east-west direction. It is usually sandwiched by upward and downward field current. So magnetic field measurement can tell the direction of convection, and by comparing the direction of bead propagation, we can check whether or not it's regulated by local convection. And another thing I'm very, very curious is the evolution of beading arc. And cinema has multiple satellites passing over oval, one after another. And for example, in the middle of beading to break up, we have undulation. And so the question is how precipitation evolved as auroral form evolved. That can be addressed if you have satellite passing the structure one by one. And another one is if it's monospheric or ionospheric, I would expect that the MI coupling is important. And for that, if we have a high resolution auroral imaging, that would be a good test of our hypothesis, whether it's a monospheric or ionospheric. And so I'm very much looking forward to which this kind of a test can be done and be realized. Thank you very much. And Slava, could you, do we still have time? Okay.
Question which,
3A, 3B.
and what about the fourth?
Fourth one is 4A.
4A.
Yeah.
Okay. So
From now on, Slava is showing 3 movies. I stopped sharing.
yes, I'll move them to a different desktop.
Okay.
So which one?
Maybe the middle one, top middle, yes.
Okay.
This is,
Bigger.
yeah, make it bigger. And this is the one example for the formation of auroral beads. And as you see that it's split into 2 arcs, but I hope you can see that beading started on the forward arc. Could you repeat again? Forward arc, but on the equator side, it just stays. Okay, and if you move to the top left one, could you expand? This is another example. And for this event, we see 2 auroral arcs from the very beginning. And you start beading along the forward arc, but the equatorial arc was not affected, at least initially, and then followed by breakup. Yeah. And the last one. Yeah, could you close the last one in some again? Okay. This is counter propagating beading. So along top forward arc propagating to the right, east, and then along the equatorial arc structure is moving westward. So it's very, very tricky. And one possible explanation is I presented could be a local structure of electric field. And
what's the spatial extent of this?
Spatial extent from
0.2 degrees.
Yeah. And the children separation is a fraction of a degree. And yes, is this was your question?
No, the spatial
Longitudinal,
the whole thing.
At least 500 kilometers, at least.
500.
Yeah, from horizon to horizon.
Oh.
And I should have mentioned, of course, you know me, and I'm just talking. but the actual hard work was done by Tetsuo Motoba, and he created a whole, wonderful figures and movies, and those movies can be downloaded from the supporting information of the papers we published. So,
Which is what I just did.
yeah. Thank you very much.
Thank you, Shin, and Adam, please take it away.
Great. Well, thank you, Sasha and Ying, for this opportunity to share. I'm excited to share some of the work that our group has been doing, looking at also the auroral bead formation evolution within global geospace simulations. And a lot of what I'll be showing here will be building off a lot of the great work that Kareem Zrathi has published in his 2020 paper. So I wanted to first start by kind of giving an overview of that process and then how we built on that and extended it. Thanks in large part to Cinema for letting us do this. So as Shin really nicely mentioned, there are still kind of a lot of different potential mechanisms that are being proposed to kind of drive auroral beads. And I wanted to, one thing that our group is doing, and I'm hoping can kind of augment and be complementary to Shin's talk, is we've been doing a lot of work trying to understand one of the important magnetospheric drivers, potential magnetospheric drivers of these beads. And one of the primary candidates for that's thought to be able to potentially drive the formation of auroral beads is the ballooning interchange instability, which can cause ripples in the equatorial magnetic field, which are about 4,000 to 6,000 kilometer scale in the equatorial plane. And you can get a sense of that scale size relative to the rest of the magnetosphere through this evolution overview plot that I've taken from Kareem's 2020 paper, where this shows the residual magnetic field, and each subsequent inset is a zoom in of this region in the near Earth scale, where you see these ripples in the vertical magnetic fields. And you can see here that these are relatively very small scale structures in terms of the global magnetosphere size. And these, I'm going to go into it in subsequent slides, but these ripples are driven by localized minimum in the BZ magnetic field, which causes the region to become unstable to the ballooning interchange instability. And Evgeny Panov in his 2018 paper took advantage of Themis observations where they're in a string of 5 spacecraft in a row to actually observed this region where you have a localized minimum in BZ, and was able to kind of quantify the extent to which that region formed and became unstable. But due to the extreme large range of scales that we're talking about here, that these tens of RE to localized minimum of about 1 RE to a fraction of RE in the equatorial plane, is extremely hard for both observations and simulations. And I guess let me take a step back, is that the auroral beads are believed to be the auroral manifestations of these ballooning interchange instability in the magnetic equator. And Shin also was extremely helpful in showing the local simulations that we've been able to use to study this instability and how it impacts the global system. And just recently, we have actually been able to use global simulations to actually study this effect, but that requires extremely high resolution simulations that Kareem published in his 2020 paper. And to just reference just how high a resolution simulations you need, the simulation that Kareem published in 2020 was the highest resolution magnetosphere simulation that were published to date. That is a factor of 2 in each dimensions larger than any LFM simulation was published, and it achieved about 300 kilometers resolution in the Z direction in the central plasma sheet and 30 kilometers in the auroral zone. So it's an extremely computationally expensive but highly resolved simulation. And in that paper, what we studied was the growth of auroral beads during a synthetic substorm, where the magnetosphere is driven first by northward IMF and then study the substorm growth phase after a southward turning of the field. this, if anyone's interested in Gamera lore, this was actually the very first paper that when Gamera was published, applied to the magnetosphere itself. So this was towards the beginning where there was, we assumed constant conductance in the ionosphere, and there was no coupling with RCM at the moment. But what's shown on the right-hand side is the evolution of the magnetic fields in the equatorial plane as a function of time after the southward turning. So each of these periods where you have a plus 15 minutes is 15 minutes after the southward turn. And you can see as we progress from A to B to C, you can see that initially after 15 minutes, it still shows predominantly kind of the effects of the northward field where you have a lot of magnetic flux built into the plasma sheet, and which is shown in red here. And then can you see my cursor? Yeah. And then also along the flanks. But as the magnetosphere is being impacted by the southward IMF, you can see the field line, the tail begin to stretch. And that's easiest to see by each of these contour lines here are regions of constant magnetic latitude that are then mapped out into the equatorial plane. And comparing panels A to B to C, you can see that the field during the substorm growth phase is getting stretched, forming these regions of depleted magnetic field, which in the residual field shows up in these darker black to gray regions here. And these form that as the field line stretches, magnetic flux is evacuated to the day side where reconnection is occurring. And these flux evacuation causes magnetic ripples to form. And this, at least on this projector, seems extremely difficult to see. So I'll go to the next slide quickly. But these ripples form during the growth phase of the substorm, and then will ultimately get disrupted as magnetic flux will get brought in from the central plasma sheet through BVFs. So there are temporary features during the substorm growth phase in this feature. So this is a little bit easier to see. What I'm showing here, what Kareem is showing is zoom in of the near-Earth residual magnetic field, and you can see again the formation of these magnetic ripples forming around a radial distance of 9 RE. I mean, you actually see that they form over a very wide range of magnetic local times, and once it replays, you can see that there are actually multiple ridges of these undulations that are forming. What is shown here on the bottom panel is the vertical magnetic field attracted along this green line at 2 magnetic local time. And this is showing the evolution of the vertical magnetic field as a function of time. So these lines are colored by time, where you're starting first about 15 minutes before the southward turning or the start of the growth phase in cyan, and then you'll go to an hour after the southward turn in this magenta line here. And you can see that during the beginning of the growth phase, we're getting the formation of these localized minimum in the vertical magnetic field, which are about 0.5 RE wide. These undulations themselves are about 4,000 kilometers in azimuthal scale. And they result from this basically localized minimum, which becomes ballooning interchange unstable. This, when you look at the video, the southward turning starts at 8 UT. You can see that it's frozen. Okay. They start to, the ballooning interchange becomes most strong at about 10 minutes after the southward turn. But if we look at this cyan line here, you can see that actually localized minimums seem to appear slightly before the undulations begin to appear in the magnetic equator. So I'll go into kind of why we think that is in the next slide. But before I do, I want to just point out that these undulations themselves are dipolarizing, similar to BVS, but they're not BVS, so they don't have very fast earthward flows. And these propagate both dawnward and duskward on the order of 10 kilometers per second. And that's a speed that's in the magnetic equator, not in the ionosphere. So that's slightly slower than typical observations that Toshi Nishimura published in 2016, which is on the order of 100 kilometers per second when taken in the magnetic equator. So the question is, why doesn't the instability kick off as soon as you have the localized minimum of the BZ form in the tail, which is ballooning interchange unstable? So what we're showing here is that works from 2D equilibrium studies is that the growth rate of the ballooning interchange instability is significantly affected and sensitive to the current sheet thickness in the plasma beta in the region where will become ballooning interchange unstable. So this work by Zhu in 2004 shows the growth rate for two different scenarios. One where current sheet is about 3 RE, which is this lower region here, and then another which they call thin current sheet, which is 1 RE in thickness. So not quite as thin as the thin current sheets that Misha, Harry, and Grant study here, but this is, in this case, just 1 RE thickness. And you can see that for the thin current sheet, the instability doesn't start to grow until the plasma beta is at least 10, and then jumps up very, very quickly from there. And in our these simulations of the synthetic beating event, right near 9 RE, the current sheet thickness is around 1 RE. So what's shown here on the right-hand panel is, again, that very same plot of the vertical magnetic field as a function of radial distance colored by time. Here that I showed previously, and on this bottom panel is now the plasma beta, again, colored by time. So you can see that as the tail starts to stretch and magnetic flux is pulled more towards the day side, you're depleting the magnetic field from those regions and thus increasing the plasma beta. So that as you progress further in time, we're below that kind of critical limit of 10, and eventually, once the undulations start to form, we have sufficient conditions for ballooning interchange to kick off, which is why it seems slightly delayed. But this also has, as Kareem pointed out, a very important impact on the rest of the magnetosphere, because it means the state of your magnetotail, both prior and during the growth phase, can significantly impact the instability and where you would expect it and to grow. So as I mentioned, these ballooning interchange heads can drive field line currents very similar to fast mesoscale flows into the ionosphere and cause kind of enhancements in precipitating energy flux. These are the auroral manifestations of the ballooning interchange heads, which form bead-like structures in the ionosphere. So what's shown here on the right-hand side is a Miller projection of the Themis ASI during an observed beating event on February of 2008, compared to the synthetic precipitation from the synthetic symptom that in Kareem's 2020 paper shown on the bottom panel. And you can see here that these, while these beads have substantially larger wavelengths than kind of nominal typical bead simulation, we're here in simulations around 200 kilometers or so. You guys see that there's strong qualitative agreement about the spacing of the widths. And I just want to point out again that this DLI simulation doesn't include any conductance or any conductance feedback from the precipitation themselves, and points to a need to kind of go even further to having greater resolution. But again, this is, I think, to my knowledge, the first demonstration that the ballooning interchange instability can create these localized BZ minimum and drive bead-like structures in the ionosphere, which is very impressive. But this is where this work comes in, so I'll try to go through this quickly, is how does the kind of formation and propagation of these beads change once we have realistic preconditioning, drift thickness, and ionosphere feedback? So in order for us to be able to answer that question, we're using the multi-scale atmosphere geospace environment model, or MAGE, which is being developed by the Center for Geospace Storms here. And in this particular simulation, we are basically using Gamera coupled to RCM in the inner magnetosphere to provide the 2D advection for the pressure and the density to drive it, to add the additional drift kinetic physics. And then this simulation also has an enhanced precipitation model where the
precipitation into the ionosphere and impacting the conductance system forward, both by the monoenergetic from the MHD simulation and the diffuse precipitation from the RCM electrons distribution. So this has an enhancement both in terms of decoupling to an intermagnetosphere model and a more realistic precipitation and conductance simulations. We applied the MAGE simulation to an isolated subtome on August 9th, 2016. For those on the cinema team, this is probably the millionth time you've seen the image on the left-hand side. I would say this is the last time, but I've also included it on my summary slide, so apologies for that. But this was a substorm that was isolated. What's shown on the top right-hand panel is the observed SIM-H and AL indices for this event, where substorm onset occurred roughly around 9:20 UT on that day. We ran the simulation with the same exact resolution that Kareem published a synthetic substormer with. So again, achieving 300 kilometers resolution in the central plasma sheet and 30 kilometers in the ionosphere. And what you're seeing on the left-hand side is an overview panel of that simulation. So first, what I'm showing here on the left-hand side is the residual magnetic fields in the equatorial plane. And then this subset shows a zoom in of the region where the ballooning interchange instability occurs on the dust side magnetosphere. So one of the key differences in this event is instead of having, with realistic driving conditions, instead of having a very wide range of the magnetotail that can become ballooning interchange unstable, we now have non-uniform kind of flux evacuation of the day side that causes only, in this run, only the dust side to be unstable, driving those ballooning interchange heads. And what's shown here, again, on the right-hand side is now the ionospheric view during that same time period, where I'm showing the field line currents on the bottom panel and the resulting precipitating energy flux on the top. This magenta line here and here, or magenta region, shows where the ballooning interchange instability maps into the ionosphere. Let me play that again. And you can see that we do, in fact, see kind of enhancements in the field line currents where those ballooning change heads, resulting in these kind of bead-like structure here. And this BZ depletion grows more pronounced and unstable, roughly 8 RE on the dust side. So very similar location to what Kareem is showing. This is just kind of more quantitatively directly connecting the ballooning interchange instability to the ionospheric view. So what I'm showing here on the left, right-hand side, the localized minimum in BZ similarly show up as inverted regions of flux tube entropy, where you have lower regions of flux tube entropy where you have our ballooning interchange stability. So you can see these kind of undulations here in this kind of dark purple region here. This green contour kind of is a way for us to mark where those ballooning interchange instability region is in the magnetic equator. And then that is the exact same contour line that I'm showing here, both in the ionosphere relative to the field line currents and the precipitating energy flux. So here you can see that these ballooning interchange heads are driving field line currents into the ionosphere, and then those upward field line currents correspond to enhancements in the energetic electron precipitating flux. And similar to what we saw in Kareem's 2020 paper is that the wavelength of these beads is around 300 kilometers or so. So again, a little bit on the larger side, kind of hinting at that we're still not kind of potentially need higher resolution in the ionosphere, but I'll get that towards the end. Oh, that is it. Yeah. So again, what I'm showing here on the right-hand side is just the propagation of those beads in the ionosphere. I'm zooming in on the small latitude and magnetic latitude local time region where these beads form. Apologies, Zoom is it's not playing over Zoom as well. But you can see that these beads, one, are persistent, so they last for about 10 minutes or over 10 minutes in the simulation. So again, a little bit longer than nominal beads, but they propagate westward, again, single direction westward in this simulation. So I'll try just a few more slides left. We can actually quantify the drift of these beads by taking elograms, very similar to actual data. And we find that these beads, so that's what I'm showing here on the left-hand side,
is an equilibrium taken directly through the beads at 67 degrees magnetic latitude. And we find that relative to when we have a constant conductance model, we actually get propagation speeds at an order of magnitude larger, so about 1 kilometers per second, which is on the lower end, but consistent with some of the statistical results that Toshi Nishimura published in 2016. And that is in large, due in part to two things. One, the enhanced conductance model, which goes to increasing the convection electric field by almost an order of magnitude relative, or a factor of 4, really, from the constant conductance model. But the convection electric field in the region where the bead's forming is about 0.6 kilometers per second. So it can't account for all of the drift speeds. So this is something we need to look into more, but this points to the importance that drift kinetic physics have, both one in kind of driving the actual formation of the beads and then how they propagate into the inner magnetosphere, which is extremely important to kind of capturing those both correctly. So I wanted to start with a question of where we can go from here. So I think both the result of this work and kind of previous work has shown kind of some of the promise that these ballooning interchange instability can have in driving auroral beads. But again, we're kind of getting to the point where resolution is extremely important, especially in the ionosphere. And another kind of layer of complexity there is that the inner magnetosphere model also has its own grid, and these instabilities are occurring in that domain. And so the combination of those can be a little tricky in terms of detailing the actual feedback between the magnetosphere-ionosphere coupling. And when we start trying to increase the resolution of RCM, this can be extremely computationally prohibitive. RCM is restricted in terms of requiring kind of a uniform grid. We can't pack cells into the auroral zone where we have regions of interest. And we'd really like to take advantage of the kind of warped 2D grid where we can kind of put grid cells wherever we need them to kind of better resolve the auroral zone. RCM itself is not fully equipped to do that, so we need a new model to do that. This is already partially solved with the advection solver from Gamer. So I know you all want to see the magnetic loop advection on a warped grid. It is, well, it doesn't posit like that. It is incredibly impressive. So what we've done, and by we, I mean Anthony Sciola, has taken the algorithm from Gamer and applied it to our new inner magnetosphere model. So we're running out of time, so I just wanted to quickly say that this allows us to a couple kind of advancements to what we currently have. As one, it allows us to have a varying cell so that we can have extremely high resolution in the auroral zone where these beads are occurring, both then mapped out into the crater, which is extremely helpful. We have better energy resolution, and then the enhanced numerics, one combines with the higher spatial resolution to allow us to kind of more accurately capture and resolve a lot of these processes, which will then hopefully allow us to kind of move closer to resolving beads on timescales and kind of spatial scales that we would expect. So I'll quickly end with that. These global simulations through MAGE were able to kind of directly capture the ballooning interchange instability and then map into the auroral manifestations of those to form bead-like structures that have nominal spatial scales and drift passes as through observations. However, I should mention, and what we know through cinema is that it's extremely hard to know if these beads require localized minimum BZ gradients, if they're necessary for these formation or not. So we really need observational studies like cinema can provide in order to help address these simulations. I'm going to end there. And
thank you, Adam, for another great talk. And the folks here will give us 2 minutes. We will open it for comments and questions from the audience. Folks, just raise your hand and ask your question. Larry, it's all yours. You will need to unmute, Larry. Larry, we cannot hear you. You
I
need
hope
to
they could-
unmute.
I hope they could hear me.
Oh, I'm sorry. I'm sorry.
okay.
My fault.
Yeah.
My simple fault.
Please go ahead.
Yeah, your simple, your model can't be the whole story, right? Because if the flow channels coming in lead to the growth of the beads, then you're not including that. And we see that really clearly in the on the auroral observations, in the electric field observations with the radars, and Shin showed it really nicely in the magnetic field how that works. But at the same time, what you reminded me of something that Toshi and I saw in one of our earlier papers, and somebody else, I can't remember his name, who was in Calgary, and that there's a pre-existing wave structure that exists, and the instability that gets set off that we see as the onset beating is an instability off that pre-existing wave that's already there. So it's just kind of off the top of my head wondering whether you might be setting off those pre-existing waves, which then become more unstable or become really unstable when the low entropy flow channel comes in and spreads azimutally.
Yeah, I think that's a good question. I guess I want to be careful and not say this is kind of the only mechanism that can drive these, but kind of one potential mechanism, and there might be kind of other drivers. And kind of in Kareem, feel free to jump in at any time. But there's also kind of situations where, at least in these runs, the kind of flows from deep in the channel weren't necessary to drive and kick off the instability. But they were capable of kind of disrupting the actual instability and ending it. So there might
also just add too,
Yeah.
real quick, there's a lot of things that are going to be changing the beta, the plasma sheet, either
Yeah.
the day-side flux evacuation, other flow channels happening at higher latitudes, and all of those that will dramatically reshape, I think, the growth properties of any existing marginally unstable structure.
Yep.
We still need to figure out, why there are conditions when the flow channels coming in do lead to the instability, and why they lead to it over here and not over there, and why it grows azimuthally the way it does, and so maybe you're onto something on trying to help us understand, why it occurs, where it occurs, when it occurs, which is kind of a major important question.
Yeah. Thank you.
Thank you, Larry. Dave?
Just wanted to point out, and these thoughts arose during Shin's talk. To keep in mind that when you look at auroral images from all-sky cameras or other imaging devices, what you're seeing, of course, is the spot of like on a TV screen. You're seeing where the electrons are precipitating into the atmosphere through acceleration processes. And we know that a lot of those acceleration processes take place at altitudes of between 1,000 kilometers and 4,000 kilometers, fast established those kinds of things, along with many other spacecraft. And so I think you need to keep in mind that while the convection that you're seeing, the motion eastward, westward, probably is magnetospherically driven, the fine scale features are most likely due to acceleration processes, as you guys have mentioned in the MI coupling regime. So just keep that in mind, and that may be the resolution for your non-conjugacy effects that showed up when Showa Station and Iceland were compared.
Yeah, I 100% agree. And as I showed, the spatial scale of auroral beads and also the potential difference across auroral beads, they are just a fraction of much larger, but still mesoscale structure, we recognize as inverted V. So a small modification of MA coupling could modify the appearance or intensity or propagation of auroral beads. So as you said, we have to be very careful for sorting out what is projected to the atmosphere from the magnetosphere. So thank you very much.
Yeah, and just a quick just a quick note regarding the Ramey data where you showed those two very large inverted V's.
Mhm.
But if you look again at the pitch angle distributions, the precipitating stuff, the 0 degree, you find that the two biggest enhancements are much smaller than the length of the width, latitudinal width of the inverted V. Those are alphanic structures, alphanic acceleration structures, and you'll see those in the energy spectrum at KeV, and you see it as brightenings or enhancements in the 0 to 20 degree, the precipitating electrons in that bottom channel. So I think some of the local precipitation that's causing these beads might be these alphanic structures.
Yeah, that's an excellent comment. And cinema has multiple satellites with excellent, particle instrument, each of satellite. So if we cross, auroral beads one after another, we can, check how precipitation is modified, for example, from galvanic to monoenergetic. And that would be an excellent target of the cinema science.
Excellent. Yep. I agree 100%. Cinema is incredibly important for this issue. Thank you, guys.
Thank you.
Thank you, Dave. All right, thank you very much. We're holding the next meeting, so we should wrap up here. Just a very quick sort of organizational comment. We've been having trouble sending SPA and JAM announcement on time, and until we have sort of a wide email list, the best way to check when the next seminar is simply to check periodically on our website, and when you connect, please follow the links there. They will always be current, and otherwise we may face some technical difficulties like we had earlier today. So thank you all for dialing in and supporting, and we will talk to you next time. Please track the announcements and our website. Thank you.